Welcome back. We are still learning about voltaic cells in this section, and the original point of voltaic cells when they were discovered and studied was that they work as batteries and they produce voltage, which we can use to do useful, interesting stuff. So if you're going to go to the trouble of building one of these, you might wonder, how much voltage is this thing actually going to give me? And we can calculate that using information out of our data book now. So these questions use the same cells as were in 211.1, so to save us a little bit of jumping around, I have copied forward the contents of each of those cells. So let's see what we can do about getting voltage, also known as electrical potential, for each of these. In this first cell, it's a silver cadmium cell, we found that the strongest oxidizer was silver ions, and so our SOA reaction was silver ions picking up electrons and turning into silver metal. And our strongest reducer was cadmium metal, which oxidized to cadmium-2 ions and released 2 electrons. All that we have seen before. Now, in the data book, if you look up these reactions, here's our silver reaction right here. It shows the half reaction that we already know, and over to the right is a number which is the potential for that half reaction. Because this is a reduction half reaction, this number is called a reduction potential. And for silver, the number in the book is 0.80 volts. So I'll copy that back over here. The silver is 0.80 volts. Now, if we look at the cadmium reaction, minor wrinkle here. Where is cadmium? There we are. The cadmium reaction in the book is listed as cadmium-2 ions picking up electrons and turning into cadmium metal, and that is listed at minus 0.40 volts, which is not what we have in our cell. This is going to complicate things a little bit. So let me just quickly put in what's exactly in the book. The book shows us CD2 plus 2 electrons, arrow, CD negative 0.40 volts. Now, there are two ways you can find the total voltage for the cell, or what they're calling the net reaction potential here. I have a favorite way, and of course I think it's awesome, so I'm going to show you that first, and then I'll show you the other way, and they do both give the same answer, so you can adopt whichever one you like better. My version is, this green thing is what's in the book. If I reverse the reaction, like I did here with cadmium, then I should reverse that voltage and get positive 0.40 volts. So if you flip a reaction, flip its voltage. And then if you want to combine these two reactions and get a net reaction, we want to add these two half reactions together. And we can't do that right now. Do you remember why? We can't add these because the number of electrons doesn't match. We have our silver reaction talking about gaining 1 electron. The cadmium's talking about 2 electrons. So to fix this, we have to double the amount of silver and the number of electrons and the amount of silver metal there. And now we can add these reactions together. The electrons are spectators, so we can chuck those. And our net reaction would be 2 silver ions react with 1 atom of cadmium metal. That gives us 2 atoms of silver metal and 1 cadmium-2 ion. For the voltages, 0.80 plus 0.40 gives a total of 1.20 volts. Now, since you just came out of the thermochemistry unit, you were probably waiting for me to double this voltage, because when we did Hess's law with delta H's, if you use twice as much chemical, you would get twice as many kilojoules of energy over on the right. That's totally true in thermo. That's not how electro works. One of the major differences here is if you use twice as much chemical here, you do not get twice the volts. What you get is the same number of volts, but your battery will last twice as long. So Train yourself on that. If you're doing a delta H, then yeah, double the reaction, double the kilojoules. If you're doing if you're an electro, double the species here or double the coefficients here, nothing happens to the voltage. And then when you add these half reactions together, you add their voltages, and this 1.20 volts is what we'd call the cell voltage, the net cell voltage, the net cell potential, some term like that. Now, if you don't like all this flippy stuff, there is a formula that does the exact same job, and the formula says the electrical potential of a cell equals the electrical potential of the cathode minus the electrical potential of the anode. And sometimes they just write EC minus EA, although EC is a little shifty because that could mean cell or cathode, so it might be better to write cath and an or something. Now, if you're using this formula, you just use the numbers out of the data book, you don't flip anything. So, for the cathode, you would say, my cathode is silver, it's 0.80 volts, minus, because there's a minus in the formula, and for the anode, you use the number in the book, which I erased it, but you remember it was negative 0.40 for cadmium. 0.80 minus negative 0.40 is the same as 0.80 plus 0.40, and so again, we get 1.20 volts for our net cell potential. So the formula way totally works. The flip and add way I kind of prefer. It makes it feel a little more like what we learned in thermo, which I appreciate. You just have to remember the exception that if you multiply a reaction, you do not multiply its voltage. So I will probably end up doing this way more often. I'll try to do cathode minus anode a couple of times to remind you that it's a valid alternative. Good. Let's do some reps and see if we can get comfortable with this. Okay, our next cell was a graphite electrode. Graphite never does anything in these reactions. It's not even on our data book list, so I'm going to ignore that. We had acid dichromate. Cr2O7. We know acid dichromate is a strong oxidizer, and I remember the iron being the reducer in here. So let's just blip over to our data book to remind ourselves about this. Acid dichromate is this row right here, Cr2O7 plus 14 hydrogens. That's the acid. Very strong oxidizer that we see a lot in our questions, and it's listed at 1.23 volts. So we can get that down. That'll be our SOA reaction, the one that happens at the cathode. Cr2O7 2 minus plus 14 hydrogen plus 6 electrons gives 2 chrome 3 ions plus 7 H2O, and that's listed at positive 1.23 volts. The other reaction was iron metal oxidizing, which is, where is it? Right here. This one is in reverse. We start with the iron metal and then it oxidizes to iron 2, and in the book it says minus 0.45 volts. So the book reaction, which is iron 2 going to iron, is minus 0.45 volts. But our reaction, we start with the iron metal, that's our SRA, and it turns into iron 2 and 2 electrons. Because I flipped the reaction, I also flipped the voltage. This is now positive 0.45 volts. I want to add these two half reactions, but I can't because what? The electrons don't match. 6 electrons here, only 2 electrons here, so to fix this I must triple the iron reaction. 3 times the iron, 3 times the iron ions, 3 times 2 is 6 electrons. Now that the electrons match, I can cancel them out, and my net reaction will be, I just add together all the other stuff. Cr2O7 2 minus plus 14 hydrogen plus 3 iron metal gives 2 chrome 3s and 7 water and 3 iron 2 ions. And when you add these reactions together, you add their voltages, and we get 1.68 volts. Multiply this by 3, don't multiply the voltage by 3. Probably okay with that. Or, if you do E cathode minus E anode, then your cathode would be the 1.23 volts minus, and in the book, the iron line says negative 0.45 volts. You don't flip it. You never flip. You just take the book numbers for this. And these double negatives mean we get 1.23 plus 0.45. So again, you get 1.68 volts. Not too bad, I hope. What else can they throw at us here? Platinum electrode in a hydrogen gas hydrogen ion solution and a zinc electrode in a zinc ion solution. So here we get our strongest oxidizer was hydrogen, reducing like so, and this is the reference cell in the data book, so I happen to remember this one. Hydrogen's exactly 0 volts. Where are we here? There we go. 2H plus 2 electrons to hydrogen. They had to pick something to be 0 volts, and they picked hydrogen because this is an easy reaction for a chemist to set up. So that's our SOA at the cathode. And the other reaction was about zinc. So the zinc reaction we found down here, zinc 2 to 2 plus 2 electrons to zinc, but we're starting on the right. So while it says this in the data book and it says minus 0.76 volts, what am I going to say now? We're writing that reaction in reverse. We are starting with zinc metal, and we're going to zinc 2 and 2 electrons, and because we're writing the flipped reaction, we get positive 0.76 volts. And we want to add these together, and usually this is where I say but in this case, they already have 2 electrons each, so wonderful. We can add these without having to fix anything. 2 hydrogen ions react with 1 zinc metal. We get a molecule of hydrogen, a zinc ion, and when we add the reactions together, we add their voltages, and we get 0 plus 0.76 is 0.76 volts. If you did cathode minus anode here, you'd be doing 0 minus negative 0.76, and you would still get positive 0.76 volts. D is a nickel copper cell, and for this one, our SOA was copper. I assume you can look this up and confirm these reactions, so I'll save you a little time. And the nickel metal turning into nickel 2 ions was our SRA. Electrons match, so we can add these together. I'm doing this in a different order this time just to show you that you can. You can get the entire net reaction written like so, and then you can go grab the voltages later. That's no problem. So we have copper 2 reducing to copper, which is right here. Copper 2 plus 2 electrons turning to copper metal is 0.34 volts. 0.34 volts. And the other reaction was nickel metal turning into nickel 2. Where is that? Here we go. So in the book, they assume it's nickel ions turning into nickel metal. That's minus 0.26 volts. If you start on this side, run the reaction in reverse, you're going to get plus 0.26 volts. Zero 0.26 volts. We didn't have to multiply these reactions by anything because they both contain 2 electrons. Not that it would matter because you don't change these voltages anyway. So when we add these half reactions together, we add the voltages and we get 0.60 volts for our cell voltage, our cell potential, net potential, whatever you want to call it. And one more of these. Graphite electrode. Graphite isn't on the redox table, so I'll ignore that. Acid permanganate is going to be our SOA for sure. We know this is one of the strongest oxidizing agents. And then we have lead. Oh, this is the one with the lead sulfate, that funny lead sulfate reaction that kind of isn't what I was expecting. So let's steal these out of the data book. Acid permanganate is our third strongest oxidizer. MnO4, 8 hydrogens, 18514. One MnO4, 8 hydrogen, 5 electrons, gives us a manganese 2, and 4 water. And unfortunately, I couldn't hold the voltage in my head at the same time, so back we go. Acid permanganate's voltage is 1.51. Hope you aren't getting motion sickness from all the scrolling back and forth. Sorry about that. I tried getting all this on the screen at one time, and it's just too cramped, so this is the best I could come up with. Okay, so that's our SOA. Acid permanganate reducing, 1.51 volts. And our SRA, you might remember, is this. The lead metal reacts with sulfates and gives us lead sulfate, and that reaction is minus 0.36 volts. But for us, and the way we're doing it, it's going right to left. We're starting with lead and sulfate, and we're getting lead sulfate here. So because we're running this in reverse, we're going to get positive 0.36 volts. So our anode reaction, the SRA reaction, will be lead metal plus sulfate ions turns into lead sulfate and 2 electrons released and 0.36 volts. It is 0.36, isn't it? Sorry. Leaky brain. Yeah, positive 0.36 after it's been flipped. Okay, so we want to combine these two reactions, but the electrons don't match, so we have to fix this, and the numbers are not going to be nice here. We need the lowest common multiple for 5 and 2, which is going to be 10, which means we have to double the permanganate reaction, 2 times that. 2 times 8 is 16. Can I make that readable? Sort of. 2 times 5 is 10 for the electrons. 2 times the manganese, and 2 times 4 is 8 water. And down here we multiply by 5. 5 lead, 5 sulfate, 5 lead sulfate, and 5 times 2 makes 10 electrons. Now that the electrons match, we can throw them away. They are spectators. And then we scribe all this tedious business out. How did I get a plus up there? I'm sorry. MnO4 is definitely a negative ion. Its charge is -1. And then we have 16 hydrogen and 5 lead. We're doing all the left side stuff. Arrow, and now all the right side stuff. 2 Mn, 2 plus, 8 water, 5 PbSO4. Electrons canceled out. And when we add these together, we add their voltages, and we get 1.87 volts for the cell potential. So if you made a battery out of these things, that battery would give you 1.87 volts. If you used, now, we're right at the end, so let me just point this out. All the time that we're doing this, the data book is assuming, says table of selected standard electrode potentials, asterisk, Scroll down to the bottom of the page. Asterisk, for 1 mole per liter solutions at 25 Celsius and a pressure of 101.325. So at ambient conditions in a slightly warm room, if all your concentrations are 1 mole per liter, this battery would give you 1.87 volts. If you make the concentrations higher, you'll get more voltage. If you make the concentrations lower, you'll get less voltage. If you change the temperature, that will affect the voltage. So there's a lot of assumptions built into this, but at least this is a start. You can figure out how strong a battery can be using a certain combination of chemicals. And we'll build more detail into this later, but for now, if you're comfortable with this, life is good. Final note, if you did this one with E cathode minus E anode, you should have gotten 1.51 for this, minus negative 0.36, and of course, same answer at the end.